Hey everyone, so my name is Phil Bedard. I'm a principal engineer here at Cisco in the Mass Infrastructure Group, and I'm also one of the architects for routed optical networking. So right now I'd like to kind of take you through a bit of the automation and how we're tackling the convergence of these IP and optical networks together in the future, and then show a bit of a demo also on how we're doing that, a bit of a lower layer view of how we're solving those problems. Just kind of as a recap of how the architectural shifts are happening and how we're enabling this. Really, the focus today for me is on this sort of change number one, and that's really moving from a external transponder-based system between IP and optical, and then utilizing what we call these 400 gig ZR and ZR plus pluggable optics in this QSFP DD form factor. The picture below is what that actual optic looks like. That's the real innovation here, because really what it allows me to do is, take what I'm doing in a coherent optic today, package that into a pluggable optic that fits in what would traditionally be like a gray optic port. We've had technologies like IP over DWDM in the past, but we always lost density on the router. There are always other types of limitations with that technology. Now, since I can use that optic in any normal port, actually it's a BDD port, I kind of eliminate that. Over time, we expect to move, what are considered, optical layer services to the same converged architecture. And then in the end, really we have this simplified, really packet fabric that we're carrying all services across. The reality today is most services are all packet-based anyway, so we have very few non-packet SONET fiber channel type services that exist today. But we're looking at ways to carry those over that same packet infrastructure as well. So when we look at kind of how we're tackling automation for this converged architecture, really wanted to start with a kind of an open standardized automation framework. I think traditionally we've had really kind of closed EMS systems per vendor, but really the idea is to move to more open standards based APIs and models for how we communicate between these different elements. And really what we're trying to follow here is what we call the IETF ACTN architecture, which stands for Abstraction and Control of Traffic Engineered Networks. And it's really a loose framework that defines a hierarchy of really controllers and orchestrators in the paths between those. It doesn't define, actual APIs or models itself. Those are kind of left up to the outside bodies to determine those. But really, it sets up a good communication flow between these elements where, you have a hierarchical controller that really handles the multi-layer provisioning and multi-layer network. And then each domain is managed by its own, what they call provisioning network controller. And you can imagine in an IP and optical networks, it's a logical separation where each one of those different domains is handled by these specific PNCs, for lack of a better word. So when we look at a few use cases, very kind of simple use cases, this is a very high level view of the ones that we absolutely have to solve in these converged networks. Obviously, link provisioning. This is turning up new links on this converged network across both the IP network and the optical network. And remember that now my DWDM wavelength endpoint is a optic inside the router. So I now need to manage that as sort of one end-to-end workflow. Like I said, when you have that optic in the router, I'm kind of bridging between these two domains. And at least for now, we look at that optic as really part of the packet domain of the router managed domain that's responsible for configuring all the other elements of the router. This is still another element of the router. The idea is to make this into a kind of a single unified workflow where in the past these were very disjoint operations between IP and optical teams. And how we've built this, we still have kept in mind that many organizations do have separate IP and optical teams. So there is options for just provisioning the IP piece of this, for just provisioning the optical piece of this, or I can do it all as kind of one single workflow. Another piece that obviously we have to cover is assurance. It's like how we get the data out of the optical network, how we get the data out of the packet network, and kind of join those KPIs, we call them key performance indicators, into a single assurance view, so you can do end-to-end troubleshooting across this new sort of converged network. Like I said, traditionally the optical folks, they have their EMS systems which are fairly closed. They're looking at all their optical parameters sort of in a silo. The router guys, they see a router interface go down that's across an optical network. They turn around and call the optical guys. Well, now it's this unified layer of the network where, they have to do more joint troubleshooting. And just from an operations point of view, we do see more combined IP and optical groups at service providers today. You really have to do that to optimize, the planning life cycles if you really want to be efficient in operating these networks. So we have seen a lot of, sort of joining of those groups today. In the future, we're also looking at ways to do kind of automated assurance to one sort of thing that's always been difficult is to map between, say, a router port and a transponder port and figure out where things are connected. So we're doing advancements in both, how we operate the ZR optics as well as the optical side to do sort of automated verification between those and discovery between those endpoints to kind of eliminate sort of that black hole of, missing knowledge in those interconnections.
So, quick question:
Yep.
as a stopgap, in a lot of cases, you have, like you said, this sort of closed optical management platform. It's probably Java. It runs over here on this thing that you have to keep safe. And now you're saying we have this other platform that kind of does everything. One of the things that those management platforms will typically provide is a bit of a fire hose of information about the optic and the transponder. So you can see, light levels, and you can alarm on changes, and you can do all the typical telco things that, alert the NOC or the first level optical team of what is going on in the network and if there's a potential problem. Have you addressed the stopgap from how it's done now to how it's going to be done in the future in this converged platform by providing some of those same type of alerting mechanisms? Do you have something better?
Yeah, so when we talk about the routers, and I'm sure you guys have seen things on, streaming telemetry and modern, the sort of streaming data off of the routers themselves. And all of the optics data that someone's used to off a transponder, like power levels, chromatic dispersion, those types of values, we can get all of those off the optics today. So we can stream all of that information, like you said, in a fire hose as much as you want. We can do it in 5-second intervals, much faster than what we were doing on the optical network. If someone wants to consume that data, and then we have applications where we can, create specifically. I'm showing the sort of automation stack today, and when you look at sort of this telemetry application in the upper right, there are sort of alerting mechanisms that can be set up. So there's thresholds that can be set based off that telemetry data that's coming in to then alert based on, say, my power level drop be, below a certain threshold. So absolutely, we can do that type of activity.
Well, that brings up another question for me in the same vein as what Nick asked. So if you're converging the IP and optical layers together, which, I agree makes a lot of sense, does that change anything for you in the realm of going into things like spans, mirrors, lawful intercept, when you're bringing those two things together in the same chassis? Is that, further enabling it, or are there limitations there when you're needing to get that out of the box?
It's really kind of agnostic to that. Like I said, the good thing about this is it's just a pluggable optic. So the electrical side interface of that optic looks like any other Ethernet optic. So in the operation of, the router itself obviously has to configure the DWDM type parameters, but apart from that, it's no different. So in the operation like span, there is no difference in that.
Gotcha. So if I wanted to mirror something that was, a coherent optic plugged in versus, a run-of-the-mill 100 gig, 400 gig optic, there's no difference as far as the router architecture. It doesn't care. Exactly.
On the electrical side, it just looks like an Ethernet interface. So that function is agnostic to what type of optic it is. So in this diagram, I show a bit of, this, when we look at this more of a hierarchical approach to controlling networks. At the top, you see EPNM, and EPNM is the Evolved Programmable Network Manager, and that is our traditional EMS system. And when I talk about this solution, we do have ways of managing all of this via EPNM as well. But we're really, focused on the future of, this more open automation framework. And when we look at that, across this, we call it the Crosswork Network Controller platform now. And we really have a series of applications that are built on that platform that handle both the packet layer of the network as well as the optical domain of the network. And the name of our optical controller is actually CONC. It's just Cisco Optical Network Controller, which runs as an app within this infrastructure. But the key part of some of we see TAPI in there. TAPI is an open standardized API for doing optical management. And like I said, the idea is to keep these APIs and models we're using as open. And on the right, I show Sedona systems, and Sedona, makes what we would call a hierarchical controller. And this is really kind of an example of one that we're doing some integration with. And they have a product called NetFusion. And we're using open models and APIs. And the APIs today is RESTconf. The industry is somewhat, settled on using RESTconf as the API that's used between all these controller elements. In the case of the packet network, we're reliant on mostly IETF models for that to convey knowledge about things like topology data. And then on the optical side, so the ONF, Open Networking Foundation, a few years ago started work on what they call Transport API as a way to manage optical networks. And it's really all aspects of optical networks, from equipment management to creating services. And there are some competing standards, but this has really become sort of the de facto standard. So when we look at Cisco ONC, the northbound side of that is TAPI, or Transport API. So that is how you interface with that specific controller. And that controller, today has no GUI, there's no visualization layer. It really is just a controller for that network that other controllers interface with. And TAPI is seen pretty widespread industry support from other vendors as well at this point. It's like I said, it's kind of the de facto standard of what's being done.
Wait a minute, you're going to take away all the TL1?
We're not taking away TL1. We're so you have to put it in perspective. We're abstracting it. So that's the abstraction layer. So ONC, when ONC talks to your actual device, it may, at the lowest level, it's still TL1. But
yeah, you can't kill TL1.
Unfortunately,
kill one TL1, two more will take its place. So for those that don't know, TL1 is the command line language / operating environment for most optical telco gear.
That was a Telcordia standard. It's 25 years old at this point. But the idea is to move to this model, and all of these different communications, they're based off really Yang models. So all of these APIs are rendered dynamically using these Yang-based models. So that's really how we're building these this communication today.
So I've got a question before you run the slide, the drawing that you had up there. As I look at the way you're separating the layers out there, you've got the overlay layer there, L3, and then going on down into the optical layer. I guess one of the questions I have, and you have the segment routing network there in the middle, is that typically if we're going to have path changes at L3, we're using things like PFT or TILFA to plan our path changes. Now that you're converging all this together, and you're not trying to guess whether or not the optical layer is up by using the L3 stack, can you inform the routing from the lower layers now that that's converged? And when you have a path break, is that something that is feasible or desired that you've done? It just has me curious that now that you have visibility to it, is it useful in mapping out the routing architecture?
Yeah, it's all about the visibility and having a system that converges those layers. And I'll show that in the demo a bit with what Sedona is doing. And that's absolutely what they're doing, is able to take all of that aggregate data and then create a network model that is aware of the other layers of the network. Where, like you said, they might have been siloed in the past. So the demo, this is done. This is in a real environment. So this is kind of looking at some of the hardware that we have today. Some pictures of that. I'll say the real key enablers are the ones in the middle there. Those are the optics and the routers. So this is a ZRP or ZR plus optic. And there's a difference between ZR is the OIF standard. Those only run at 400 gigabit. They're single wavelength. ZR Plus was created as a more flexible option to ZR. And ZR Plus optics, can run at 100, 200, 300, and 400 gig at different, modulations for those that are familiar with for optical. And the big reason for that is really distance and reach. 400 gig ZR optic is really spec'd to run about 120 kilometers or really 80 kilometers at a maximum. So it's really for shorter metro type point-to-point links. ZR Plus, we just did a test in our internal lab of running one at up to 1,250 kilometers. They use different FEC formats, and there's different things that enable that. And you can read all about that on the OpenZR Plus MSA page. In this demo, we are using the NCS 2006, traditional kind of optical line system. This is a kind of an overview of our full topology. And really the focus of this demo is across a single pair of routers, a single span or optical span on that network that we'll really focus on. But we have a number of ZR and ZR plus links, at different points in this network, as well as optical nodes to really stress test the technology. We've been testing this for about 2 months now. And we continue to test, sort of newer variations and newer hardware revisions. We take a look at that sort of the span that I focused on. This is kind of what it looks like. So we're using the Cisco 8000 series routers. As mentioned, these are 1RU routers. They're 24 by 400 gig, and you have some. I think it says 12 by 10 gig should be 100 gig ports. But these use a single 10.8 terabit NPU. So there's just one NPU on this device that powers that entire amount of bandwidth. And as mentioned, we're using our ZR Plus optics. And in this use case, we really just have a couple of wavelengths that we're multiplexing. We call this the MD64 multiplexer, and it's really just a passive multiplexer that's multiplexing these wavelengths into a single common signal that we feed into the optical system. In this case, this is a 64-channel mux. The amount of bandwidth we need, the optical bandwidth for ZR Plus is about 75 gigahertz. So on a single span today, we can multiplex 64 in the C-band. If you add the L-band, you could potentially do another 64 channels. You can imagine that's quite a bit of bandwidth. 64 400 gig interfaces is quite a bit of bandwidth, and we have yet to really run into too many providers today that exceed those types of bandwidth values.
So because I think people probably aren't familiar with it, can you give like a 30-second overview of the C-band and what the C-band and the L-band is?
The C-band is sort of the traditional band that's used, and the best way is to probably look on the ITU's website or Google C-band. It's really a band that's, and I don't know the exact sort of wavelengths that covers specifically, but the C-band was like I said, sort of the original, and today most systems can do 96 channels. If you're talking about like say 100 gig wavelengths, support say 96 channels, and that fits within kind of what we call the ITU grid. The L-band is really created because people are running out of wavelength capacity on spans. And that's when we look at things like 100 gig or even 10 gig wavelengths, single channel wavelengths, it's pretty easy to exhaust the wavelength capacity. So really we want to look at the L-band, which is L-band is another set of sort of non-overlapping with C-band wavelengths that we can then further multiplex onto a single fiber to get that sort of, at least in this case, 128 channels.
So basically the theory here that I'm trying to express is that you have a fixed number of resources, and the C-band and the L-band sort of define what those are. And in optical networking, those are wavelengths, right? So they're essentially frequencies that can be used to put services over, and you have a fixed amount of those. Now, if you translate that to say like enterprise networking parlance, and people are going to cringe when I say this, but like if you think about it, like I can run 4,095 VLANs on this switch, but I can't run 5,000. It's conceptually similar. You can only run X amount of wavelengths based on their channel width on a given transponder.
Yeah, and that's why we really see like the move from transponders to this packet architecture. So I get the benefits of stat muxing. That's a huge benefit. With a transponder, I'm really mapping a fixed 100 gig channel. And sometimes I can map that to a 250 gig or 400 gig single wavelength. It's not very efficient use of the resources. We moved to packet and stat muxing for its efficiency or even oversubscription capabilities at most areas of the network. And optical, I'll say in the past, optical has kind of outpaced the bandwidth of what we're doing on the electrical side or on, let's say, the router, IEEE interface side. That's not quite the case anymore. But in this demo, I've got a couple of amplifiers and then a 50-kilometer span that's a mix of actual real, fiber optic spools as well as some attenuators to add, some loss to simulate distance in the link. And one point is, with this, we're not completely eliminating the optical network. To use a span greater than, to use a 120 kilometer span, it needs to be amplified on both ends. To use something greater, we still need amplifiers in the middle. We still have multiplexing components. So some of the complexity of the optical network doesn't go away. So we still need to manage that through the automation tools. So now I'll quickly switch to the demo here. So what I'm showing here is actually not a Cisco tool. This is Sedona's NetFusion product. And what I'm looking at is a multi-layer representation of my packet and my optical networks in my lab. In the black there, you can see the optical network. It's highlighted, it can isolate to just that layer. And then I can see the packet network as well by looking at that view. I think the key point with this to note is that it's not going directly to the devices. It's not using TL1 to the routers to get this information. It's getting all this information through those standard APIs and models. So that's really sort of what we're trying to enable through this, more controller-based architecture is, using open standards to then integrate, platforms like this, into that. And if I do changes to that network, they'll be reflected in here kind of almost immediately. And that's something kind of we'll see as we go on. If we take a quick look, this is a view of CNC, or Crosswork Network Controller. And like I said, it's really a platform. And what we're looking at here is an application within that. So in NetFusion, we were looking mostly at the infrastructure layer of the network. This is kind of taking things a layer above that and looking at the traffic engineering view of the network. So I've got segment routing policies that are running end to end on my network, and I'm utilizing the so when I create these SR policies, they're managed through CNC today, and I can see I've got one SR policy end to end across the network here. It's taking a bit of a long path around the network. We look at an SR policy; it's defined by a few key parameters: the head end, the end point, which is the tail end, and then we call a color. That denotes the, sort of the application treatment of that policy or the constraints of that policy. So I'm taking this long path around the network, and you can see looks like there would be a good path between these two routers on the network that's not up today. And that path, corresponds with the optical layer that I showed in NetFusion. So if we take a look at, yes, this path from A to Z takes quite a long path around the network, and it's really just using the shortest IGP path today to do that. So like I said, if we take a look at NetFusion, the same two routers are the ones between Los Angeles and Phoenix, but I have an optical path, but no circuit that rides between those two routers along the optical path. If I look at NetFusion, I can kind of see the same view of the network in NetFusion. It's again learning all of this information through CNC, our controller, through standard models, as well as in this case a couple of proprietary models. You see the same segment routing path with the same color going through the network.
So, quick question. For your segment routing, are you using typical BGPLS and PCEP to do the learning and the heavy lifting?
Yeah, so if we really took it, what's below the CNC layer of the network, so CNC is talking to our what we call SRPCE. SRPC is learning the IGP topology, and then we have, via BGPLS. So we're using BGPLS from the network to SRPC.
Okay.
Take that a step back, and then from there, we use a REST interface in SRPC to convey that knowledge to CNC.
Okay.
And then obviously CNC is using a standard topology model then for this information to go to NetFusion.
Okay. So for those that are listening that may not be familiar with SR, basically BGPLS is BGP link state, and it allows a controller to learn the real-time link state of a topology so that it can then inform where it wants to push its label switch paths to. So its LSPs are then provisioned based on that information and can be re-provisioned based on changes.
Correct. Yeah. So in this case, you can apply certain constraints. In this case, it's really just shortest IGP path that we're following across the network because we don't have this direct link. And I'll quickly work through, how we're enabling sort of a single workflow to then create these links across the network. And for that, we're using NSO. So NSO is Network Services Orchestrator. And we've created a number of service types specific to routed optical networking. The real basic one is actually creating just a simple circuit between two routers. And we're doing the provisioning on both the routers and the optical network. This includes the ZR plus provisioning, as well as creating the optical circuit and the optical system as well. And we're doing that using Transport API. So we're using the same type of open interface to ONC to create these circuits through NSO. Like I said, I'll kind of step through here, and you can kind of see I've got a very simple service defined. There's only a few key kind of input parameters to this, like the frequency. You have to have the wavelength you're using, as well as things like the grid type and the bandwidth. So the bandwidth really sets the mode. In a ZR plus optic, that can be 1, 2, 300, or 400 gig. With ZR, it's just a single one. And I've got a couple of devices that I've defined for this. These are my two endpoint routers for the circuit. And then under those, there's really only a few parameters that I define. In this case, I can define IPv4 addresses, as well as things like the other mandatory part that I have to define is the ports that I'm using on that router itself. And we refer to those as the line port, which is more of an optical terminology. But that specifies sort of the line port or the optics port that we're using. So once I have these defined in NSO, I can look to commit that. We do validation checking. So in this case, I forgot the line port config on one specific one. And typically with NSO, you're not interfacing with this UI. Typically, you're driving this via a northbound RESTconf interface. So what this is doing is just rendering a service model that's written in Yang. But typically, we can do this type of provisioning through NetFusion as well, if that's the route that you want to go through. But this is kind of showing the lower layer information of how we're doing this type of provisioning. So once I revalidate that, I can commit this to my network. Take a look at the config that's being deployed. Once it's configured, I could go ahead and check to make sure that this is in sync and it's properly deployed. And this is all to be driven through a northbound API as well. It takes about 90 seconds for a coherent optic to come up. So once I've provisioned the DWDM parameters, it does take time. So I figured I'd show a bit of sort of the background of what's being created. Like I said, these are all open models. Example of a TAPI model. TAPI uses something called a connectivity service. That's really the open model for creating all kind of what we call circuit services in TAPI. In TAPI itself, if you take a look at it, it can be quite complex. It's really meant to be consumed by controllers and machine-to-machine communication. We wouldn't expect a human to really write some of these RESTconf calls over time. So I guess it's really meant to be driven by a controller, which is what we're doing. If we take a look at sort of some of the IETF L3 topology data that we're conveying between CNC, this is an example of a RESTconf call to CNC to get sort of what we call the IETF topology data, where we get all of the link information, IP address information, as well as we have some extensions to SR as well to get segment routing information through these topology models. And these are all based off either RFCs or drafts that are in progress that we're actively committing to.
So real quick, can you give a 30-second overview of what those extensions to SR entail?
On the SR topology side, so the way that this RC 8345 model is built, there's a base model, and then I can extend that through augments. And the SR model today, what we're covering is basically like node SIDs, adjacency SIDs. So in the notion of that model, there's links, there's nodes that are already predefined. So I'm augmenting those, let's say, containers in Yang with specific SR attributes, like the SID information. So that's some of the information that we're conveying today. What we're working on is a way to extend those to SR policies or SRTE. Today, that it really only covers the base kind of SR MPLS IGP information that's advertised. It doesn't really cover SR policies. So that'll be another extension to probably a different, I'll say a different model in the TEAS, the Traffic Engineering Working Group, in order to extend that to support, traffic engineered SR paths.
Yeah,
So
that would be very rad if it did the SRTE paths.
yeah, it's kind of been a missing
When?
piece. Yeah,
Yeah.
because RSVT is there today and support for that, but not SRT is a bit missing. So just to quickly, if you, I've switched back to NetFusion, and as you can see, I now have a link between those two nodes. So NSO has gone ahead and created that link. And all this information is so we're using subscriptions and notifications. So this is not like a 5-minute polling based operation that happens. So most of this information is conveyed sort of automatically or very quickly. So a link comes up, a link gets added to the IGP topology. CNC learns about that from the network, and it automatically pushes that to NetFusion through subscription-based notifications through RESTconf. So we could take a look at the path of this one, and as you can see, it's taking a much longer path for this specific hop because it's showing both the IP and the optical view. So the question about multi-layer and how I can converge these layers. So now in this single router hop, I not only see the Ethernet information, but I also see the optical information. So I know exactly which optical nodes and path this is taking end to end.
Can you drill down there and get more information out of those?
Potentially, yes. Yeah, if I clicked on one of these elements, I could see more information. And then if I take a look at my segment routing path, I could see that now my path is actually taking the shorter path across the network. So it's switched to this shorter link instead of the long sort of convoluted path it was taking. And then I could also, if I look at the SR path, I can also see the optical information that, so I have to expand the view a bit so you can really see the end-to-end view on this one link. I can see the SR path, the IGP path, as well as the optical network that this is going across. And again, all this information is conveyed from our controllers to NetFusion, which is correlating this data and creating these different routes across the network. Here's kind of my last slide. We talked a little bit about telemetry data and the kind of the telemetry data that we get off of the nodes themselves. This is just a Grafana dashboard to quickly illustrate that. But you can see that we're getting sort of all the relevant data that people typically want from an optical network, such as the TX power, the RX power, the bit error rate. We are using, forward error correction with coherent DSPs. The modulations, this is 16 QAM. Decoding that, there's always errors. We can't enable this type of technology without forward error correction these days. But it's good to monitor that and make sure that the post-spec bit error rate is 0. You always want that to be 0. But these are the different kind of values that we get. and there's many more as well that we get off the optics to sort of monitor these and potentially alarm on these when there's issues that happen. So you kind of see over the last 15 minutes, things are a little more stable on the network.
So I'm curious, going back to the controller, the PSAP controller that you had and RSVP-TE, does that allow you guys to stitch together policies from the two different worlds? Because I know, one of the things I spend a fair amount of time on these days is migrating off of RSVP-TE and onto SRMPLS, ISIS, and moving that ISP's policies for traffic engineering onto those architectures. Does putting all of this into the same orchestrator and giving that visibility down, does it make it easier to join those two worlds, since I see that you have RSVP-TE and segment routing there in the same controller?
Potentially. Interworking between the two, that's something that's pretty difficult to do.
Sure.
But at least visualizing and seeing the path of like a higher layer across each of those segments is definitely something we can do by sort of joining all this data together. Absolutely.
And that was kind of the core of my question are you doing it now, or if you're not doing it now in the future, is there a potential for that interop? Because obviously you don't exactly have the protocol interop, but with the advantage, a third-party controller, you possibly could stitch an end-to-end policy together as more of the network gets converted to segment routing versus RSVTE. Really, that's what I'm curious about.
Yeah, it really requires like what we consider a multi-domain PCE. And a product like NetFusion does have that capability. So I could create an RSVT engineered path in one domain. Where those interconnect is, sort of the hazy point, but we can also, do that sort of inter-domain computation to at least pick what we would think would be the best interconnection point as well. So yeah, it's definitely, the capabilities are there.